Okay, so this is lecture 6.2. This is the second lecture of chapter 6 of the group theory course. Chapter 6 we started in the last time. It's about applications of group theory to selection rules and direct products. We have discussed in the previous lecture the direct product between two different groups, and today we start by discussing the direct product of two irreducible representations of a group. So the direct product of two irreducible representations, it's easy to define because it's simply the direct product of two matrices, which is a very well-known operation from linear algebra. So you define a certain matrix element of the product matrix C as the product of, in a proper way, of the matrix elements of matrices A and B. So this represents the direct product C of two matrices A, B. And if you remember the direct product, so if you have to multiply the dimensions, right? So if A, for instance, is a 2 by 2 matrix and B is a 3 by 3 matrix, then the direct product matrix C is a 6 by 6 matrix. So and this is a way to define the direct product between two IREPs, two irreducible representations. Okay, so there's this theorem that says that the direct product of two representations of groups A and B, you take two different groups and take two representations, one from group A and the other from group B, this will form a representation of the direct product group. So and this is a simple proof. I'm going to skip that. You can read that proof in pages 101 and 102 from the textbook, but it's very straightforward from linear algebra by constructing this matrix elements of the product. So if you are interested, you can look it up, but it's important. This is an important result. Okay, so instead of doing the proof, let's consider a simple example, which is this one. This is a group D3. This is the character table of group D3, and we have seen this sometimes already. We can construct the group D3D as the direct product of group D3 with the inversion group. If you remember from last time, the inversion group has only two operations, identity and inversion. It's also called sometimes the CI or the S2 group. Okay, and it has only two operations, E and I, and two one-dimensional classes, AG and AU. We're gonna use these symbols many times, G and U for G for even and U for odd representations, and this comes from the German names for even and odd. Okay, so whenever you see an index U or G, you know that you have an odd or an even representation under inversion. So you can see the characters here. For the even representation, it's even under inversion, so it's +1 here, and for AU is the odd representation, so it changed sign. The character is -1 under inversion. All right, so let's see then how will you construct the direct product group D3D I think we've seen this last time also. You take all the symmetry operations of the original group. We have identity, threefold rotations and twofold rotations. These are the symmetry operations of the original group, and you combine them with the inversion. So we have an extra set of classes, 3 classes. You have originally 3 classes, now we have a total of 6 classes because you combine the original classes with the inversion. All right. So IC3 is an improper rotation, and IC2 prime, it's a reflection plane. Okay. So now you have 6 classes, and you also have 6 irreducible representations, which now again you can label them and classify them according to whether they are even or odd under inversion. So originally you had 3 irreducible representations, A1, A2, and E, and now you have A1G, A2G, EG, A1U, A2U, EU, and these are even and these are odd under inversion. Okay. So let's see. Let's apply this result that I have discussed before and see how one could construct the matrices, the representations of the product group D3D, starting from the representations of D3 and the inversion group. Okay. So for the one-dimensional representation, this is trivial because the matrices are just numbers, and you only have to multiply the numbers. Okay, so you essentially for you multiply this A1 and A2 to construct the even representations. You multiply by this line 1 1. And to construct the odd representations, you multiply by 1 minus 1. Okay, so that's why you have this is precisely the same as this. These 2 blocks of the character table are the same because these 2 characters are both 1. And for the odd representations, this is the same as this again, but this has minus sign everywhere because you multiplied by minus 1 here. Okay. So this is how the character works. But let's see how for the 2-dimensional representations, how one could get those starting from the D3 group. For the D3 group, if you remember, you have used this as an example many times. We have constructed the matrices for this E representations, for the 2D representation. And these are for the identity and for the C3 rotations, and this for the C2, the 3 C2 prime rotations. Okay. So if I want to construct now matrix representations for EG and for EU, again I have to multiply by the matrices, which are essentially numbers because you have only 1D representations here. We multiply by the matrices associated with AG and the AU representation. Okay, so essentially that means that for the EG representation we don't change anything, and for the EU representations, you take all the symmetry operations that are you combine with the inversion, and you apply a minus sign for the C3 and for the the EU representation. So these are the matrices for these 3 different classes, and for these other 3 classes you basically multiply this matrices by minus 1. All right, all the elements by minus 1. and that's the result of that operation. Okay. All right. So. Okay. Now, I see. Okay, so let's now consider the direct the characters for the direct product. How do we obtain the direct product? The characters when you have direct products. In both cases, we have considered direct product of two groups and direct product of two representations. Okay, so let's see how we find the characters, and this is a theorem which is it's stated in a funny way, which is the following. It basically says that the simplest imaginable formulas for the characters of direct product groups and direct product representations are assumed. What does he mean by that? It basically says that when you have the direct product group, when the direct product of two groups, then the character for the irreducible representations of the direct product group for two given operations A, K, and B, L are simply given by the product of the characters of the original group. Okay, so in the direct product group, the character associated to a certain symmetry operation, which is the product AK times BL, it's simply the product of AK in the A group times the character of BL in the B group. You simply multiply the two characters. And the same thing for two representations of the same group. So the character for the direct product representations is the product of the two original representations for a given symmetry operation of the group. So again, let's see how this works by example. Once again, I'm not going to prove that. You can see the proof in page 103 of the textbook. Again, let's see how this works by considering again the D3D group, which is the direct product of D3 and the identity, and it's similar to what we have considered already. You can see that the product of, for instance, you take representation of the product group EG, which is the product of two representations in the original D3 group and the AG representation of the inversion group. Okay, so this is the AG representation of the inversion group, and you multiply that by the, for instance, the E representation of the D3 group. And if you want to see what the characters are, you simply multiply the characters. So the characters are, since the AG representation, both characters are 1 here, and you see that the EG representation has precisely the same characters as the E representation in the D3 group. So another example is, for instance, EU. EU is equal to the direct product of E and AU, right? So the characters again are going to be the product of the characters. So this is this times 1, and this is this times minus 1. All right. Okay. So and let's explore other possibilities. For instance, let's look at how one can make direct products of representations of the same group and see what we get. For instance, let's take the group D3D and let's see, for instance, what do we get when we take the direct product of 2 representations of this group, EG and A2G. Okay? So if you want to find the characters, we can basically use this theorem that we have stated here. You just multiply the characters of both representations. So when you do this, basically A2G is 1, 1 minus 1. You have to multiply by 2 minus 1, 0. So let me write this here. Let me go back here. I want to calculate many products of representations. For instance, I want to multiply EG and A2G, and what is the result of that? So we multiply basically 2 numbers. This is 1 times 2 is 2, this is minus 1, this is 0, and this is 2 minus 1 and 0. So and if you, this is going to give you either a representation of the group, irreducible representation of the group, or a reducible representation, a representation that you can reduce. So just by looking at it, you can see that this is essentially equal to EG, right? So the product of EG and A2G is EG. So what about EG times A1U? Again, you make the product of the 2 characters, so 2 times 1 is 2, then this is minus 1, this is 0, and now you invert the sign, right? So it's minus 2, 1, and 0. So what representation is that? You can see that this is essentially the EU representation, right? So it's not an odd representation. So this is something that we're gonna see many times in the future. When you have the product of 2 even representations, the result is also an even representation. When you have or a combination of even representations. And when you have the product of 2, so 1 even and 1 odd representation, then the result is an odd representation, or it can be decomposed in a sum of several odd representations. And you have, when you have odd times odd, you also have even representation. Okay. Now let's do a slightly more complicated case. Let's take the product of EG and EU. Again, you multiply the characters, so you have here 4 1, 0, and minus 4, minus 1, 0, right? So this is certainly not an irreducible representation of the group, because it's a four-dimensional representation, but you can notice that you can write this as a sum. Well, let's see if we can guess that without decomposing using the formula. We can guess, first of all, we know that the product of even and odd representation must be a combination of odd representation, right? So it must be a certain combination of these three odd representations: A1U, A2U, EU. And you can basically guess and notice that this is actually the sum of the three. So this is AU plus A2U plus EU. Okay, and you can check that this is correct. Okay. All right, this is an example. So let's now do another example, which is this one, the C4H group. The C4H group is a direct product group between C4 and inversion. And once again, you can see that again you have even under inversion representations, AG, BG, and EG, and odd under inversion, AU, BU, EU. And these you can divide the character table in blocks. These three blocks are essentially the same as the C4 group, and this block here is essentially minus sign everywhere. Okay, so this is very common, and we're gonna see that many times. All right, so another example that I want to discuss, and this is to make a connection with things that we have discussed in chapter 5, is the full rotation group. So the concept of direct product tells us how, using the same kind of idea, how do we get the characters for instance, improper rotation. Sn is an improper rotation. Basically, you rotate by a Cn and combine this with a sigma h reflection, and this improper rotation can also be seen as a combination of this is not 100% correct, so this is I will call it C alpha. So it's a combination of a rotation of an angle alpha with the inversion, but then we have different cases depending on the angle. So you have to think about it geometrically, how you do this operation. But if you think about it, you will see that, for instance, let's take S6. S6 is a combination of S3 and inversion. So that means that the angle alpha that you have to use in this formula here is 2 pi over 3 for S6. For S3 is a combination of a C6 and inversion, meaning that the angle alpha is 2 pi over 6. Finally, S4 is actually a combination of C4 and inversion, and so in this case the angle alpha is pi over 2. Okay, so we have to be careful in choosing the correct value for the angle alpha depending on the case here, but the idea is the same. So you combine the character for the rotation, which is given by this. This is the character for rotation that we have discussed maybe 2 lectures ago, and this is the character for inversion, and then it will depend on the value of L. If L is even, then it's even under inversion, so this is equal to 1. And if L is odd, this is odd under inversion, so this is equal to -1. So this is how you construct the character of an improper rotation. And also mirror symmetries, reflection symmetries. So reflections you can always combine with C2 operations. So reflection is equal to a C2 combined with inversion, right? So using the same argument, you can remember. So what is the character in the full rotation group for a C2 rotation? So a rotation by pi, right? So this is the same equation, the same formula. This is the sine L plus 1/2 pi and divided by sine pi over 2, which is 1. So this is -1 to the L. Okay, so when you combine this with the character for inversion, which is -1 to the L, then the character for sigma h is always 1. So this is the result that Marcus has shown us today in the group. So this is always 1, and it doesn't matter what reflection operation you have. This is also the same for a diagonal plane or for a vertical plane, because you can always take these different planes and construct these reflection operators as combinations of a given C2 axis and inversion. So this is another important example of applications of this idea of combining or multiplying characters of 2 combined operations of product groups to form the characters of the product operation. Okay? All right. So let me now go back to the main topic of this chapter, which is trying to calculate matrix elements such as this one. So this is, we have discussed last time, this is a typical problem that we have. We need to calculate matrix elements of this type, where H prime is a certain perturbation Hamiltonian that will or will not couple initial and final states. And as we discussed last time, the typical example is the electromagnetic interaction in the dipole approximation. So what we have discussed also last time is that this is non-zero. So this is a constant, right? Because this is a number. So, and this number will be independent of the particular choice of axis of coordinates that you use to calculate it. So this should be invariant for any symmetry operation of the group. This is the same as saying that this transforms like a constant. So it transforms like the identity representation of the group, right? Okay, so let's see in terms of group theory how we analyze this. Okay, So you want to calculate matrix elements of this type, and let's say that we have these two states, psi alpha I, which is a partner alpha of a certain irreducible representation gamma I, and similarly phi alpha prime I prime is another basis function, is another partner of a partner alpha prime, right, of the irreducible representation gamma I prime. Okay. All right. So and also the perturbation Hamiltonian H prime, it also has symmetry properties. You can, maybe it's a function of a sum of different functions that will transform like another representation of the group. So let's say that H prime transforms like the irreducible representation gamma J. Okay? So in terms of group theory, the product of these three quantities being transforming like a constant means that when you make the direct product of these three irreducible representations, gamma I, gamma J, and gamma I prime, this must contain the identity representation. The identity representation. Okay. So sometimes, or most of the times, this product of representations will not be an irreducible representation of the group, but it will be a reducible representation. But the idea is that when you decompose into irreducible representations, one of the terms must contain the identity representation, so that otherwise this quantity is zero. Okay. So another way to see this is by looking at this sandwich here as the scalar product between psi alpha I and the vector H prime phi alpha prime I prime, and this, it will be non-zero only if, so this transforms like gamma H, this transforms like gamma I prime. So this will be non-zero only if the product between gamma J and gamma I prime contains the irreducible representation of psi alpha, which is gamma I. So okay, so in terms, we're gonna see how this works by doing several examples today. Let's see, going back to the specific Hamiltonian that most of the times in this case we are interested into, which is the electromagnetic interaction interaction Hamiltonian in the dipole approximation. So this is involves the momentum operator P and the vector potential A of the electromagnetic field. So, but in terms of group theory, this is essentially a constant. So this quantity will transform like a vector, like the P vector, which has 3 coordinates, Px, Py, Pz. And this quantity transforms like any vector x, y, z. So whenever you want to see what representation is associated with the transformation properties of the electromagnetic interaction, you basically have to look in the character tables what irreducible representations transform like the XYZ coordinates. Okay, so let's do an example, which is the cubic group. Let's take the electromagnetic Hamiltonian and let's look at possible optical transitions between different states in a cubic environment, in the OH group. Okay, and let's take, for instance, let's take the case in which the initial state has a T2G symmetry. Okay, so let's take the case in which the initial state has T2G symmetry. And so let's see what would be the possible final states that will couple to this initial state under the action of the electromagnetic field. All right, so this is the character table of the OH group. This is a slightly different notation. Instead of A1U, A1G, so on so forth, it uses plus and minus signs. But this is the same idea. So T2 plus means the even under inversion representation. So this is in another notation. This is T2G. Okay. This is T2G. So this is our initial state. And okay, so following the ideas that I discussed here, I basically have to make the direct product between the vector and the initial state and see if it contains the final state. That's the idea. All right, so let's look here and see where the XYZ coordinates are. So the XYZ coordinates are here. It's right here, T1U. It's a three-dimensional representation. It's a 3D representation. And you see the coordinates of a vector here, x, y, z. So, and another important point is you see that the vector is always odd under inversion. So you always find the coordinates when the group has inversion symmetry. You will always find the x, y, z coordinates somewhere here in the odd representations, never the even representations. Okay. Okay. Now, so what we have to do now is to make the direct product of these two representations, the vector T1G, sorry, T1U, and make the direct product with the initial state representation, which is T2G. Okay? And again, you do that simply by multiplying the two characters. You take the characters here of this line and multiply by the characters of this line. So in the end, you have 9, 1, minus 1, minus 1, 0. And since I know that this must be an odd representation, because it's the product of an odd and an even representation, I know that for the other classes, the classes in which I combine with inversion, I know that I must have only simply the minus sign here. Minus 9, minus 1, 1, 1, 0. Okay? Okay, so this is the characters of the direct product representation. So, and now I have to decompose it, right? So I can either try to guess by looking at the character table. In this case, it's not so simple. Or I use the decomposition formulas that we have discussed already. So I'm going to skip this part and simply give you the result. And the result of that is the sum of A to U plus E U plus T1U plus T2U. And again, you notice all these are odd representations. Why? Because you have the product of an even and an odd representation, and the resulting representation must be a combination of odd representations. Okay? So, and initially I had a nine-fold degenerate, a nine-dimensional representation, and this is split into a 1D, a 2D representation, and 3D representation. So the sum of dimensions here is also 9, and then this is consistent. Okay. So, and all right. So what is the conclusion of this exercise? The conclusion is that when you have an initial state of a certain Hamiltonian in a cubic group, in the OH group, and the initial state has a certain symmetry, which is in this case is a T2G symmetry. It's an even state under inversion. So this will only be able to make optical transitions in the dipole approximation to states that transform like A to U, EU, T1U, with these different sets of states that have these specific symmetries. Okay. Again, and this is another very general result. Since the vector has, the momentum transforms like a vector, which is it's odd under inversion, so it will always couple initial and final states with opposite symmetry. So if the initial state is even, the final state is odd. If the initial state is odd, the final states are even. Okay? All right, very good. So let's do another example. In this case, let's see what happens when if we lower the symmetry of the cubic group to tetragonal. Okay, so if you, for instance, if we apply some strain in the material and you reduce the symmetry from cubic to tetragonal, and let's see what happens then when you now have the D4H group. D4H is tetragonal. This is not the character table for D4H, but it's the character table for D4. But once again, the character table for D4H is just a combination of this with the reflection sigma H. So it's the direct product of these two groups. So it's the direct product with inversion too. So this is D4H it's equal to the direct product of D4 with the inversion group. And once again, when you do this, I'm not going to write it here, but remember, you're gonna have now, instead of 5 irreducible representations, you're gonna have 10 irreducible representations. Half of them are going to be even, and the other half are going to be odd under inversion. Okay, and you also have the twice the number of classes. All right. So what's important here, if you notice here in the character table, is that now when you break the symmetry, and now you have the z-axis is not equivalent to the x and y axis, right? So now you can see that they belong to different representations. The z coordinate is here, and the xy coordinate is here. And you have to remember that this is the D4 group, but if you make the table for the D4H group, they are both going to be odd, right? So because the x, y, z, they are always odd under inversion. So the z coordinate will be a basis function for the A to U representation, and the x and y coordinates are going to be partners of the two-dimensional EU representation. Okay. So now these are the vector representation now is, which originally was T1U, now is the sum of A2U and EU in D4H symmetry. Okay. All right. So now again, let's suppose our initial state has E2G symmetry, for instance. If our initial state has E2G symmetry, we have to see what are the possible final states. We have to make this direct product of E2G and the representation of the vector, which is the sum of E2U and EU in this case. Okay, and so this is then the sum of these two products. EG times E2U is EU, and EG multiplied by EU is decomposed into these 4 different one-dimensional representations. So I'm not doing this calculation, I'm just showing you the results. But this is basically saying that if your initial state has 2G symmetry, the final possible states are, they may have these different symmetries: EU, A1U, A2U, B1U, B2U. Okay, so you see that things are starting to get more complicated when you reduce the symmetry, and this is a very general statement, and it happens many times. When you reduce the symmetry, the number of possible transitions increase. Okay, so before in the 4H group we had only 4 possible symmetries for the final states, and now we have 5 possible symmetries. This is a general remark. Whenever you reduce the symmetry, the number of possible non-zero matrix elements, the number of possibilities increase. Okay, for optical transitions. Okay, now finally, to finish this lecture, let's discuss about possible polarization effects. This is also very interesting, and group theory is very powerful in giving us some indications of how one can change the selection rules by changing the polarization of an electromagnetic field. Okay, so let's consider two cases. Still, let's consider the D4H group, but now let's say that the light we shine into the material is not unpolarized. So the previous situation we have considered is for unpolarized light. Now let's suppose the electric field is polarized in the z-axis. Okay, so and if you remember here, the z function, the z basis function is right here. So it's associated to is a basis function of the A to U representation. So now our Hamiltonian will not transform like the sum of E to U and EU, but it will transform just like the A to U representation. Okay, this is the symmetry of the Hamiltonian H prime. It's A to U. Okay, so again, going back to the same formula, essentially what I need to do now is to ignore this part, and basically what I have now is that if my initial state, this is the symmetry of the initial state, if my initial state has EG symmetry, my final state must have EU symmetry only. So it's more restrictive. Okay, if I know the polarization of the light, there can only be final states with EU symmetry. Okay, and then I can repeat this exercise for many possible initial states. In this case, there is a one-to-one correspondence between initial and final states. So if the initial state, for instance, is A1G, the final state has to be A2U. Okay, so when the electric field is polarized in the z-axis. All right, so this is so again, this is showing you how group theory is powerful in determining these selection rules. Okay, very nice. So let's now consider a more complicated case, which is the following. What if the electric field is polarized in the x-axis, along the x direction? Okay, now let's go back here to the character table. I reproduced the character table here. If you look, the x coordinate is right here, is one of the partners of the E, in this case EU representation. Okay, so the x function is actually partner of EU. I will call it UX. The other partner would be Y, right? Okay. So now we have to consider the possible initial and final states. Let's see what happens if the initial state it's the totally symmetric representation A1G. Then this gets so the final state must be the final state must be one that contains the direct product of E1 EU and A1G, and this is simply EU. Whenever you make a direct product with the identity representation, you get the same representation, U in this case. Okay. So, but I mean, is it possible to say something beyond that? Yes, because if you see the initial state, sorry, your Hamiltonian transforms like just one of the partners, in this case the X partner of your EU state. So then, in order for the matrix elements to be non-zero, the final state must also transform like the same basis function X. Otherwise, the matrix element, the scalar product, would be zero. Okay. Let's see now if the initial state is A1U. Now, in this case, I have to make the direct product between EU, AA1U, and the result is EG. So EG, again, is it the final state must be EG, but is it possible to say which partner of EG is selected in the final state? Yes, basically, if you look at the basis functions for EG, I don't have here the full character table of D4G, but I'm saying to you that these are the two basis functions for E2G. It's X, Z, and YZ. Okay? These are even under inversion, these two basis functions. So these two basis functions of EG are X, Z, and YZ. So what happens in this case is that the final state must contain the same coordinate X. Otherwise, the scalar product is zero. So in this case, the final state is EG XY. Sorry, XZ. So sometimes it's easy to figure out, sometimes it's not so easy. But by looking at the basis functions, sometimes it's possible to see what are precisely the final state that you have by looking at the precise basis functions associated to the initial state, and also by looking at the symmetry of the perturbation Hamiltonian. Okay? Alright, so this is the end of chapter 6. We have 3 problems, 6.1, 6.2, 6.3. This is the problem set 6, and this is for next Monday, okay? For next Monday, April 20. Alright, thank you.